our domains in our first units, which would be polynomial functions and then rational functions. For polynomial functions and for rational functions, the domain problem was very different. Polynomials and lots of other functions that are not polynomials have a really basic domain of all real numbers, or negative infinity to infinity. Okay. And so when you're looking at just a polynomial, which is like in case one where you've got just a sum or difference of powers of x or powers of some variable, your domain has nothing to worry about. It's negative infinity to infinity. Because when we're talking about our domain, I'm going to put this word in quotes. The domain basically describes what are we allowed to plug in for x, or what kind of numbers, if we plug them in for x, will give us y's. In a polynomial, there's nothing holding you back from what you plug in for x. Now, some numbers are harder than others. You're like, I don't really want to plug in, 32/7, but you could, and you would get an answer. There isn't any number with a polynomial that if you plugged it in, for some reason, you'd come back undefined. So basically, that's what we're looking at when we talk about a domain is, what am I allowed to use for x so I don't get anything, I don't get the function to be undefined. I want to stay away from functions that are undefined. Let's keep it defined. Domains, the numbers in the domain are the numbers that keep the function defined. So polynomials, everybody plugged in, anybody we want to plug in keeps it defined. There's only 2 times we have to worry for algebraic functions, for the function to become undefined. One of the things we can't have is if we have a denominator in our function, i.e. a rational function, we can't have the denominator of that rational function equaling 0. That's a bad thing for the domain. That's a number that won't work. Those are numbers we kick out of the domain. And we spent a big chunk of time when we did rational functions, and I'm going to make a little note here, all these fraction functions are called rational functions. As we worked with rational functions back in our second unit, that was the very first thing we talked about. What numbers would make the denominator 0? Because we built our domain out of everything except those numbers. Okay, so let's go ahead and do that over here. I've got 2 rational functions, a and b. On the first one, we're going to think about that denominator equaling 0. And that's kind of the ironic thing. We don't want the denominator to be 0, so we basically have to think about what would make it 0. It's like, okay, what's bad so I can skip it. So on this one, I have to think about this. What will make that denominator equal to 0? Okay. That's the thinking that I have to do to build that domain. Okay, where's my little grabby thing? Oops. Nope. Oh, there it is. Okay. Miss Schweitzer made this note handout. She must write little because I don't write that little. She did 2 little problems in that box, and I can't do both those problems in that box. So I'm going to go into a new page. All right. So I'm going to think about x squared plus 5x plus 6 equals 0. It's a quadratic. when we want to find zeros of a quadratic, factoring is a good strategy, especially when you have an x squared and then a linear x. So let's see. Quadratic formula can work, but we hate that. If we had a graphing tool, we could graph it and the zeros would be the x-intercepts. We would love that. That's super fun because it's easy to graph. This actually factors pretty nice. X and x. And 2 and 3. And two numbers that multiply to 6 and add up to 5. And then from the factors, we get the roots, or the numbers that make the polynomial equal to 0. So x plus 2 equals 0 means if I subtract 2 from both sides, x is negative 2. And then the same thing with the negative 3. So then, what you got to remember is, why did we do all this? Because we wanted to find out, these are the numbers that we're going to kick out of our domain. We're going to exclude these numbers. They can't come to our domain. They don't make this function defined. If I plug in a negative 2, it's going to make a 0 in the denominator. That's not going to make this function work. If I plug in a negative 3 into this function, it's going to make a 0 in the denominator. This function is not going to work. So how do I do it? Well, I start from negative infinity, and then as I'm going up from negative infinity, the first number I'm going to get to that I need to skip over is negative 3. Negative 3 comes before negative 2 across the number line. And then between negative 3 and negative 2 is okay. That's always the part that we forget. We're like, okay, I've got these two bad numbers, but the guys in between the two bad numbers usually are still okay. Bad numbers to the left of negative 3, bad numbers above negative 2, or good numbers below negative 3, good numbers above negative 2, good numbers in between, negative 3 and negative 2 are just the bad guys. So that's one way to write it. And my end infinity always ends up looking weird because I run out of room. Or another way to say that, my domain is all the real numbers, negative infinity to infinity, any number you can think of that's a real number, except these two. In calculus, we talk about domains multiple ways. Sometimes we write them in intervals, and sometimes we talk about them more in words, like I did with the all reals. Either one is appropriate. This interval notation kind of goes right back to what we were doing with that piecewise function, because it's saying, okay, I can use negative infinity, I can use everything up to negative 3, I can't use negative 3. I can use negative 3 to negative 2, but not either of those numbers, and I can use negative 2 to infinity. All right. All right, we good on that one? Yes. Now, just because I have a denominator doesn't necessarily mean the domain is going to kick numbers out. And that's what problem B is about. I have a denominator here of x squared plus 3. And so I'm going to think about x squared plus 3 equal to 0. And if I just stop and think about that, I'm going to square something and add 3 to it and end up with 0. That only would work if I could square something and get -3. Now, in terms of real numbers, that can't happen. Positive numbers squared make positives. Negative numbers squared make positives. 0 squared makes 0. There isn't any real number that I can square and get -3. I would need an I, an imaginary number, to make that happen. So there's no solution to that. There's no way to make the denominator 0. So in this problem, in B, I'll write a little next page here, the domain ends up being -infinity to infinity. I went looking, I'm like, okay, the troublemakers are going to be the things that make the denominator 0, but this denominator is never going to be 0, because x squared can never be -3 with real numbers. So cool, all real numbers. If the denominator can't be 0, then you don't have a problem. Everybody's good. All real numbers are good. -infinity to infinity. Okay. So first thing we're going to worry about when we look for domains is denominators. Domains and denominators. The second thing we have to worry about is we can't have a negative number under a square root. Now, technically, you can't have one under any even root, but at this point, really, square root is the main root we work with. But if we were going to do like 4th roots and 6th roots and 8th roots, we would have the same thing. Square roots are really kind of if you know what to do with a square root, you know what to do with all the rest of the even roots. The bottom line is you can't have a negative under there. You can't take the next square root of a negative. Once again, square root of a negative requires imaginary numbers. So when I have a square root, that's what I have to worry about. I have to worry about keeping what's under the root from being negative. So whatever's under the root has to be greater than or equal to 0. Now, sometimes that's easy. When what's under the root is a linear expression, something with just an x, not an x squared or x cubed, but just x plus 3, 2x minus 5, 7x plus 47, whatever it is, taking something like that, x plus 1 greater than or equal to 0, you solve that just like you solve an equation. We would subtract 1 from both sides. X has to be greater than or equal to -1. So in domain terms, it's everything is good starting from -1 going up. So I can start from -1 and go up, and that's my domain. Everybody from -1 on. Not the whole number line, but the chunk of the number line that starts at -1 and goes to infinity. So let's stop for a minute and summarize kind of what we said so far. If we're finding domains, regular polynomials, yay, -infinity to infinity. And we know like sine of x and cosine of x also work that way. E to the x works that way. We have a lot of functions out there who have -infinity to infinity for their domains, and we love those functions. They're super fun, and they're easy to work with. Messy functions, what makes things messy? Well, one of the things that makes things messy is a function that has a denominator, a rational function, because you can't let that denominator be 0. So if it can be 0, if it's possible that that has solutions when you set your denominator equal to 0, then you've got to kick those guys out of the domain. Not every rational function does that. Sometimes you have a denominator, but it can't be 0. It'll never be 0 with real numbers, so everybody's good. Other messy sloppiness, roots, specifically square roots, the fact that you can't take the square root of a negative. So anytime I have a root, I'm going to look at an inequality problem. So it's two different attacks. It's sort of when we have the denominator and the domain problem, we've got to equal to 0, or think about the denominator equaling 0. When it's a root domain problem, we think about being greater than or equal to 0. And as you can see, we're going to put those two ideas together. It's actually not that big a deal to put them together. What is the hardest, I think the hardest part of this, and this is the newer part, is when I put something under a root that's not linear. Okay. I'm going to make a little note here. This guy was linear. Just an x, or an x to the first power. Both of these guys, B and C, have a quadratic, or an x squared, under the root. And that is where we're going to have to do the most work. All right, but we can do it. It's not that we can't do it. It's just, it's like yucky. It's like, ugh, okay. Linears, easy. Under roots, who cares? Just treat them x plus 1 greater than or equal to 0, la, 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 just like an equation. However, quadratic under the root, here's going to be the fun part. That's what we have to think about. But I already taught you how to do that. I know you're like, no, you didn't. Yeah, I did. We learned about something called a polynomial inequality that involved number lines and testing numbers. This was a long time ago, back when we first got together in September and we were in Unit 1. We did polynomial inequality. It's probably one of the first really hard things I taught you, or tried to teach you, where we worked with factoring and testing numbers and making the number line and what's positive and what's negative. Okay. So I'm going to write that down here. We're going to attack this using our strategies that we learned about with polynomial inequalities. And I know in your head you're like, I didn't learn those. Yes, you did. You knew them for a while. But knowing that that's not something that always sticks, and also knowing how important it is for calculus classes, that's why we're talking about it again. Okay, so here we go. Polynomial inequality work. First thing we do is we do roots. So we set it equal to 0, and we factor. And look, this is the exact same one we did from before. So we can kind of just cut to the chase a little bit. We know what, we already thought through the factoring. And got these roots. 0, factor. Okay. Next thing I'm going to do, I'm going to put these roots on a number line for myself. And I'm going to use this number line to sort of organize information about my function. I'm going to try to decide if each section of this number line represents a section where the function would be positive, or does it represent a section where the function would be negative? So each section, this section of the number line, this section of the number line, this is the one that's going to be yucky, this section of the number line, I'm going to pick a number in that section, any number I want. I'm going to think about plugging it back in to the function, and I'm going to figure out if the function would be positive or negative with that number plugged in. Depending on what that number does, that makes this whole section follow that same behavior. Sometimes we made charts for this. We might do like write our factors down. And this is going to be for the answer. And these are the numbers I'm going to pick. And I always go weird. I'm like, -10. That's way down here, right? If I put a -10 into each of these factors, -10 plus 2 is -8. -10 plus 3 is -7. So a -10 plugged into each factor makes both factors negative. I multiply two negative factors. This is for answer. I get a positive. So positive answers, positive function values are going to come out of this section of the number line. All the numbers in this section of the number line plugged into this function are going to make the function positive. When we finish doing this analysis, you'll see we are going to be interested in the positive sections. Positive sections are the ones we're excited about. Positive sections are going to be my domain sections. Now, it's always tricky when there's two numbers that are kind of close together. You got to go in between them. So -2.5 would still make that negative, but -2.5 and 3 comes out positive, and a positive times a negative is a negative. I think you might remember we figured out a lot of these polynomials alternate behavior. They go from like above the x-axis to below the x-axis to above to below. They curve back and forth, and that goes from positive outputs to negative outputs to positive. So we get a lot of alternating. If it's a double root, sometimes that's where we might get positive and positive in a row. But we have in the past, if we've seen these, we've kind of, if we weren't sure what to do, we're kind of like, it's probably going to alternate. Let me just guess. And so if this is positive, you would guess that this is negative, and you would probably guess that this end part is going to be positive. Let's pick something down at that end part. Something bigger than -2. Okay, how about +10? +10 is definitely going to make both of those factors positive, which makes a positive answer. Yeah, polynomial inequalities are work, for sure. And we use them in calculus all the time. I say out of all the things we did in this class, this is the thing we're going to use. One of the things we're going to use more than anything. So, what the heck did that just tell me? Well, positive is greater than 0. These numbers are the equal to 0 parts. The positive sections are what's going to make my domain. And so after all of that, the domain for this particular function is negative infinity to negative 3 with a square bracket, because negative 3 is included. We can equal 0, and negative 3 will make it equal 0. Union, square bracket, negative 2 to infinity.